Okay, good morning. Let's get started. People will keep coming in. So yesterday we looked at an introduction to computational neuroscience, history of computational neuroscience. Then we looked at the signaling in a neuron, the neurophysiology of a single neuron. Then we put it into a mathematical form and derived the Hodgkin-Huxley model. Then subsequently we looked at some simpler neuron models because Hodgkin-Huxley is biophysically quite detailed, but if you just want to look at the input-output behavior, you can manage with much simpler neuron models like the Zykevich neuron and leaky integrate fire neuron and so on. And afternoon, I'm sure you have done some practical sessions on various kinds of neuron models. Now let us take it up from that point and then see how you can use such neurons and construct networks. So typically you can proceed in two directions once you understand Hodgkin-Huxley model. So you can even go deeper into biophysical neuron models, study what happens at subcellular level, and look at how signals propagate inside an axon, inside a dendritic cable, and so on and so forth. You can go even more detailed. But we haven't done that in this course. So we will only look at now larger scales from now on. So we have seen the Fujinaga. I'm sure you have done some practical sessions on Fujinaga model, Morris-Lecca, Rizikevich models, and so on and so forth. So now what we'll do is from this point onwards, we will look at a single neuron model, which is called the McCullough-Pitts neuron model. So yesterday at the end of Hodgkin-Huxley, what we have seen is this is the neuron. Input is a current. Okay, output is a frequency. Output is a frequency. Input is a current. But a neuron receives input from many other neurons. And in fact, the current that we talk about, it comes in the form of inputs from many other neurons. So you can think of all of them as inputs coming from many other neurons. You can think of them as X1, X2, some Xi, Xn, and so on. And each of these inputs comes via synapses. So you know that synapse can be weak or strong and so on. So you can think of some kind of a synaptic strength, right? W1, Wi, Wn. So the sum of all of them, sigma Wi Xi, is some kind of current. You can think of it as current. So if this total sum, if this current crosses some threshold, there is some firing response. So if you look at the Hodgkin-Huxley, we derived through empirical studies a curve which looks something like this. This is the current, this is the frequency, and there's no frequency at continuous firing up to a point. After that, it suddenly rises and then goes off. Okay, the curve ends after some time, but when you imagine it goes on and on. So, for example, for the leaky integrated fire neuron, the curve looks like this. Okay, so total sum of the current is this, and then there is a threshold term, and then there is a frequency or some kind of response or output. Now, with just these elements, we'll ignore all the biophysical details, ion channels, and receptors, and all that stuff. Just try to put together a very simple model which captures these basic ideas. And that model is called McCullough-Pitts neuron model that looks like this. So you basically combine these two pictures into one picture. And what you get is a neuron which takes inputs from many other neurons. The inputs are X1, Xi, Xn, and so on. And the weightages are again W1, Wi, Wn, and so on. So you combine all of them, you sum up all of them. That is your sigma I runs from 1 to n, Wi, Xi. If the summation crosses some kind of a threshold, because you see in Hodgkin-Huxley there's a threshold. Only after that threshold there is a firing response. So this is the threshold or bias term B. So if this argument is positive, then there is a output, otherwise output is zero. So basically so the ideal function that you can use for this purpose, this G function, should be a step function, ideally. But people also use a smoother version of it, which is called the logistic function. And that's given by this formula. I'm writing it here. Y is equal to 1 by 1 plus x power minus, e power minus lambda x. So if you plot this, you will see that y as a function of x looks like this. If lambda is a small positive number, it will be a smooth curve. If lambda is a large positive number, it will be a sharper curve. As lambda tends to infinity, this curve tends towards an ideal step function. It's basically a smoother version of the step function. So Macaulay and Pitts proposed this way back in 40s, 1943. Their objective is to understand how brain works, right? And using that kind of a neuron model. Their approach is to think of brain as a big Boolean circuit, right? Basically, they were thinking of brain as a computer because uh, brain is an intelligent organ, and the only intelligent machine that people knew at the time and even now is a computer. So because in 40s is the time when these guys wrote the paper, the World War II was going on. And at that time, they had this huge computer built. I think it's somewhere in University of Pennsylvania, I think. It's called ENIAC, Electronic Numerical Integrated Computer. So this machine was being used to send secret codes and or crack secret codes of enemies or plot missile trajectories and things like that. So they thought since computer is so successful, so powerful, they thought brain also must be working on similar lines. And therefore, the neuron is like a system, computer is basically a big Boolean circuit. There's a mathematical basis. So they thought brain is also like a big Boolean circuit, and neurons are like logic gates. It's a great insight. It's a very good starting point, although we see very quickly that that's not completely true. There are some important problems with that kind of an approach. So anyway, so they've taken the neuron as a logic gate and shown how the same Macaulay-Pitts neuron can be used to implement the three fundamental logic gates: AND gate, OR gate, and NOT gate. So if you see how, let's see how that can be done. So OR gate, the truth table is shown on the right. X1, X2 are two inputs, and output is Y. So it's a two input neuron. Basically, take an input neuron which is just two inputs. The truth table for OR gate is 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is 1. So even if one of the two arguments is 1, the output is 1. So how do you get that using this neuron? So G is a step function. Look at this expression, G of x1 plus x2 minus 0.5, right? Which means W1 is 1, W2 is also 1, and bias is 0.5, B is 0.5. If you do that, even if one of x1 and x2 is 1, the argument is positive, so Y is 1. If both x1 and x2 are zeros, then argument is negative, so therefore Y is 0, because that's the step function. So similarly, if you want AND gate, so basically AND gate, in the AND gate, output is 1 only when both x1 and x2 are 1s. So therefore, here again, W1 is 1, W2 is 1. Bias is now should be greater than 1. So let's take 1.5. So in this case, so the argument is positive only when both x1 and x2 are 1s. So this expression matches the AND gate truth table. If you want a NOT gate, the input is only one input. And if input is 0, output is 1. Input is 1, output is 0. So G of minus x plus 0.5. So in this case, bias is minus 0.5. And there's only one weight, let's call it W, that's equal to minus 1. So if you do that, you can easily see that if x is 1, argument is negative, so output is 0. If x is 0, argument is positive, so output is 1. Okay, so you can trivially show how you can implement all the three logic gates using this neuron model. So I propose that the brain is a big Boolean circuit and so on. But it's a very compelling idea, quite an attractive idea, but it's not quite correct. Why is that? Because there are fundamental differences between how a computer works and how brain works. Let's see some differences. So computer consists of rigid inorganic 2D sheets of matter because the circuit boards or the chips, they're all two-dimensional sheets of matter. Brain is three-dimension volume of tissue. It's not sheets of matter. Although one interesting thing is in brain also very often neurons are laid out as sheets. The sheet may have typically multiple layers of neuron, but there are layers of neuron like sheets. And these sheets are connected by large three-dimensional bundles of wires. That's how brain is. So it is still quite different from the anatomical, microanatomical organization of the brain. Of the computer. Now, when it comes to power supply, computer is powered by DC mains. Power is DC. Where in case of brain, it is powered by blood supply in one sense at a large scale. At a microscopic molecular level, it is supplied by power is supplied by the ATP molecules. So it's quite different. So signal, if you look at, if you tap computer anywhere, right, any bus or any wire, if you tap it and then measure the signal, the voltage value, it looks like a bunch of rectangular pulses because it's a digital signal. On the other hand, if you tap anywhere in the brain, any axon, typically axon, or even single neurons in the cell body, the signal you will see looks something like this. You'll have 100 millivolts pulse style signal. So you have series of action potentials. Right, the single action potential duration is pretty much fixed, but the duration interval between one action potential and the next one, that's quite variable. So it is nothing like a digital signal. It is some kind of a pulse signal, or there is again, so it's a modulation. Some analog signal is modulated in terms of a pulse signal. So there are many different kinds of pulse-based modulation. This is uh, pulse frequency modulation, or pulse interspike interval modulation. So it's definitely not a digital signal. Then another major difference is extreme sensitivity to faults in case of computer. If you give a computer a chassis on your table, a good shaking, it will stop working. Whereas with brain, you in a fit of anger, you bang your head on the table or something. Still, you might feel slightly lightheaded for a few minutes, but after that you are okay again. So that's very different. I'll show you some dramatic examples of this difference. Where in one case there was an accident and a crowbar goes through the head and the person still survives, right? And whereas in case of a computer, if you drive a crowbar through the chassis, and that's the end of story with the computer. So extremely fault tolerant, that's the brain, but extremely sensitive to faults, that is computer. So fundamentally, there's some difference in design. The design is totally different. And when it comes to frequencies, there is a huge difference. In computer, the clock cycles now are like we're talking about nanoseconds and all. So it's right. It's like very fast. Whereas in case of a computer, in case of the brain, the highest frequencies run into a few hundred hertz. And that itself is quite rare because if you look at the labeling of frequencies, you go from, let's say, low gamma, high gamma, that's about 100 hertz, 150 hertz, something like that. Right? Not usually beyond that, you don't have names. Is at least in popular literature. So it's many orders of magnitude slower than the computer. But thing is, brain makes up for that low speed by having massive parallelism. Because in a computer, you can have whatever, 32 GPU, 64 GPU, whatever. Whereas in the brain, you can have 100 billion units. So in fact, one of the highly parallel computers that I have seen, there was one which was released in the 90s. It's called Thinking Machine or something like that. It had 65,000 processors. It's a 2D array of processors. So that's still, that's highly parallel, but there's nothing compared to the computer. So it's quite different in that sense. In a computer, you have a centralized clock, all signals right on top of that centralized clock. In case of brain, there's no such centralized clock, and any clock-like timing, right, or pace setting happens by in a democratic fashion in the computer by these neural oscillators talking to each other and training each other. Sometimes a central pool of neurons can entrain a large number of distributed set of neurons. Like for example, thalamus setting the pace for the cortex, or subthalamic nucleus setting the pace for many other nuclei in the brain. So that kind of thing can happen. It's very democratic, not like computer where there's a military command from a centralized clock and all signals right on top of it. And when it comes to power dissipation, again, power dissipation levels in the computer is very small. I mean, amazing, miraculously small, because a normal adult brain uses about 60 watts or 50 watts and things like that. It's like almost a light bulb kind of power. Whereas if you want that kind of a processing in an artificial machine, you will talk about kilowatts and megawatts of power, and we also need huge cooling systems and so on. It gets very messy the moment you talk about power consumption levels in a modern computer. Now, another most important difference between the two systems is computer is programmed, whereas brain learns from experiences. But then with the new AI, then that also learns from experiences by training. And with agent models, they can also figure out how to teach them, how to train themselves, and so on. So we are coming very close to how brain works. But all that is because of, by the study of brains, right? Brain has inspired all these technologies. So Buckle and Pitts made a good start, but their approach is wrong because they thought of the brain as a computer. So the other guy called Frank Rosenblatt has seen this problem and said we can use the same neuron model and make it trainable and not just program like what McCullough and Pitts has done. So he said you can take a neuron and train it. So that he called a perceptron. So how do you train this? So here is a McCullough and Pitts neuron model at the top. Now let us say I want to train this on some pattern X, right? And so it is, since output can only take two values, 0 or 1, the X is mapped onto only two values, 0 or 1. So it's basically like classifying X into two categories. Is it one category or zero category? So that's all it can do. Now, how can you train it to do that? So the general approach to this can be seen in this block diagram in the bottom. So think of the single neuron inside this box, okay, and I'm cutting the box across with an arrow, just to indicate that the network inside is trainable. It is a variable. So input is X, output is Y, and I want for a given input X, output I phi to be equal to some desired value or target value. So I'll call that T. Okay, so this T and T minus Y, look at T minus Y, the error. If both are correct, then the network's output is correct. So there's no need for changing the network. If both are different, then there's an error, then you feed that error into the network, in this case, a single neuron. Change neuron's parameters in such a way that the input leads to correct output. And how do you do the training? It is like this, so delta, so shown on the right side, delta Wi is equal to eta times delta times xi. So delta here is the error, that is T minus Y or D minus Y. If you are using the notation D for desired output. Xi is the input, right? And so Xi is the input, and so eta SC is called the learning rate. Okay, so how do you get this? The logic is very simple, and we'll keep using this even for larger networks. The goal is to make sure that the desired output D is equal to Y. Okay, or one way to express same thing is define the error or squared error as E is equal to, here on the top, T minus 5 whole square. Or let's put a half here so that the half gets cancelled when you differentiate this. So you have to minimize D minus 5 whole square for all the patterns. So you have patterns like XP, that's a pth pattern. Output Y is the pth output, YP. And that summation over P, or all the outputs, square output errors, should be minimized, right? So how do you minimize that? So how do you minimize the error? So this one way to do it is simply differentiate error E, so that is dou E by dou W with respect to all the weights. Set it to 0 and then solve for it analytically, like what I'm showing here. But that may not be possible if your E is very complicated function of W and B. So what people do is do a numerical solution, do it iteratively. That is, think of E as since it's a quadratic function, think of it as like looking like a bowl, like what is shown here. Now, how do you change the Wi so that you go to the lowest point of the bowl? So how do you do that? So let's say your initial Y will be some random, so initial Wi is some random Wi. The question now is, do you move left or do you move right? How do you decide that? So you see that in this case, I'm on the right of the minimum, and so I have to move to the left. That means I have to reduce Wi. How do you decide that? Note that the derivative slope here is positive. Okay, and I'm supposed to move left, right? Now, in the other case here, I am on the left of the minimum, and here slope is negative, and I have to move to the right. That means increase W. So simple thumb rule here is, if your derivative locally is positive, then decrease W. Derivative is, if it is negative, increase W. So basically, the delta W should have opposite sign of derivative. So the same thing is valid even for n dimensions. So when you have and look at this in terms of vector derivative, that's gradient in all directions. Then again, same thing. So delta W is equal to so minus of dou E by dou Wi, or in vector terms, delta W is proportional to minus del E, that's the vector derivative of E with respect to W vector. So the same logic applies to even bias. So basically, it's the same thing. It's a very simple principle. If you have parameter which you need to minimize, the change in the parameter delta W is proportional to minus of dou E by that parameter, dou parameter. So this is called gradient descent, and we'll keep using the same principle even for much larger networks. This is derived for a single neuron. Now we said this neuron maps input onto two outputs, 0 and 1, because G is a step function. So how exactly does it map? Just see this. So there are points in the state space, input space, where output Y is 1, points where output Y is 0. So how exactly does the neuron divide this input space into two halves? So let us see that. To understand that, let us consider the boundary between these two regions. Right. So boundary is so when you know that when the argument is positive, Y is 1, or argument is negative, Y is 0. So which means at the border argument will be 0. Right. So when is argument 0? That is delta Wi xi minus b is equal to 0. Right. That's when the argument is 0. So if we just take two variables, x1 and x2, when the argument is 0, that means w1 x1 plus w2 x2 minus b is equal to 0. That's nothing but a straight line. So the boundary between y equal to 1 region and y equal to 0 region is a straight line. Okay, so the neuron basically is dividing the input space using a straight line into two semi-infinite halves. Now, if you extend this to multiple dimensions, then you can easily imagine that the neuron is dividing the input space into two semi-infinite halves using a hyperplane, right? So of dimension n minus 1. So in this case, line is a hyperplane of dimension 1, okay, which divides a two-dimensional space into two semi-infinite halves. Okay, so now with this learning rule, let us apply the same neuron model to a familiar problem. Earlier for OR gate, we just set the weights by hand like this. W1 should be 1, W2 should be 1, bias is 0.5. But if I don't know those parameters, and if I have to get them by training, how do I do that? So further, take the same truth table. Okay, so I randomly take some initial weights. W1 is 0.2, W2 is 0.3, B is minus 0.2. Okay, so if you just write the decision boundary using these parameters, it looks something like this. See this blue line in the bottom, which means it is dividing. So there are 4 data points for the OR gate, which are shown here. The 3 x's correspond to value D is equal to 1, output is 1. The circled point here corresponds to value D equal to 0. So which means the decision boundary should be somewhere here, like what I'm showing with the red line. Okay, this is the line that separates the 3 crosses from the one circle. But actually, because the weights are random initial values, the decision boundary is somewhere here, outside all the 4 points. So it is wrong. So you start with that. Now present 0, 0, wrongly classified, because this point, for this point, it should be on the left or below the decision boundary, but whereas actually it's above the decision boundary, so it is wrongly classified. Now let us look at 0, 1, which is this point. Okay, and that's correctly classified. Then look at 1, 0, this one, that's also correctly classified. Then look at 1, 1, which is also correctly classified. So out of 4, 3 are correctly classified, so performance is 75%. Okay, now you apply the weight change by learning. So then the weights change to these new values, 0.2, 0.3, and B is 0. When that happens, so the line jumps from the previous position here to this position. You see that already the line is dividing the points correctly, right? It is separating all 3 crosses from the single circle. So now you see that the 0 is correctly classified. 0, 1 is also correctly classified, 1, 0 also, and 1, 1 also. So you see that just by one single step of training, the neuron is able to learn the correct classification. So you can also see that in this case, the whole goal of training is to divide and separate the three crosses from the single circle using a straight line. And for this problem, you can easily see that there can be infinite number of such lines that can separate the crosses from the single circle. So network, as it learns, it will just discover any of those lines, and after that the training stops. So the infinite solutions are possible. But you see that this can happen only if for certain kinds of data sets. That means the data set it's not necessary that it's possible to separate the two classes using a straight line. So as you can see in this example, on the left side you see the data set consists of two classes consisting of represented by the green circles and the blue dots. So there is a straight line, or there can be many lines which can separate these two data sets, right? But on the right side, you see again the green circles and the red blue dots. You cannot separate them using a straight line. No matter how you draw the line, it won't be able to separate these two data sets. You need to have a curve, right? Which means the data set on the left side is called linearly separable classes. It consists of linearly separable classes, but on the right side, the data set is not linearly separable. Since the single neuron or perceptron can only separate or learn to classify linearly separable classes, right? It will be able to learn the left data set, but it won't be able to learn the right data set. So that's the weakness. So therefore, if you give it a gate, logic gate like XOR gate, so it will learn AND gate, OR gate, and NOT gate, which is quite trivial, so it will learn it well. But if you take something like XOR gate, so XOR gate, the truth table is like this. For 0, 0, it is 0, 0, 1, it is 1, 1, 1, it is 0, 1, 0, it is 1. So if you plot this pictorially, you will have something like this. These are the green circles and blue dots. So you see that no matter how you draw the line, you cannot separate the green circles and the blue dots. So therefore, the perceptron will never be able to learn this task. It will keep going round and round. So that is the weakness of perceptron. But good thing is it will converge if the data set is linearly separable. It will converge just in n-max iterations, and there's some estimates of how many steps it needs to converge given eta and so on. So all this we don't need this. Skip this. Okay, so there was some like that. There were some good things about the perceptron, which is that it can learn, and very interesting learning algorithm. There's a systematic approach to deriving the learning algorithm. All that. One more elegant property is what is called it satisfies the locality principle. What does that mean? So if I want, so this is a neuron, and I want to update the weight here. To update the weight, what do I need? Delta W is equal to eta times d minus y times xi. So to update the weight here, I need information about d and y. And physically, if you think of this as a physical neuron, the inputs are available at this and lower end of all these weights. The output y is available at the output end of all these weights. The target information or desired information d is also available at the output neuron. So if I want to update a given weight wi, I need information from its input end, that is xj, right, or xi, and the output end, that is y and d. Okay, so whatever information a weight needs to update itself is present exactly at its two ends. Its output end has d and y, input end has xi. Okay, so that means all computations are local. To update a given weight to implement learning, all the computations required are local, which is a very nice property of this neuron. But the main problem is it can learn only linearly separable classes. That is, if the class data is implicitly separable by a hyperplane, right? Only then the perceptron will learn. Otherwise, it won't converge. So these two people, Minsky and Papert, wrote a book on perceptron. In that, they talked about its merits, but also they highlighted its disadvantages and demerits. And not only that, they made this kind of a damaging statement about their capabilities. They said the single layer perceptron is so limited in its capabilities that it may not be worth studying its multi-layer counterparts. So because it's so weak, there's no point looking at larger versions of this network. That was the comment they made, but they were totally wrong about that. because subsequently people looked at multi-layer versions of it and found them to be very powerful. So because of this kind of a damaging criticism that levied by Minsky and Papert in their book, which is titled Perceptrons, there was a lull in this kind of a neural network research for almost a decade, more than a decade. The perceptron was proposed in 60s. 70s was a totally dull period, not much has happened. Or something has happened, but it was ignored and not noticed until the 80s came. In the 80s, suddenly people woke up and started looking at neural networks again, and a lot of progress took place. So let's see how that happened. So the 80s, people started looking at what is called as multi-layer perceptron. This is what we call deep network these days. Just the terminology has changed. But those days, they would call it the multi-layer perceptron. The idea here is in case of perceptron, there are just two layers, input layer and output layer. In case of a multi-layer perceptron or an MLP, you need to have one more layer between the two layers. This intermediate layer is called the hidden layer because it's kind of hidden from the view. The access to the network is only through the input layer and output layer. Between that, you can have one or more hidden layers. So they're all hidden from outside. And there also you have neurons and they also have nonlinearity. And usually the nonlinearity is a smooth sigmoid kind of nonlinearity, the logistic function. You can use logistic function or you can use the tanh function. Both are smooth versions of hard limiting nonlinear function like step function and signum function. So this is a hidden layer, input layer and output layer. So with this kind of a thing, people found very quickly that the problems we face with perceptrons suddenly disappear when you add a hidden layer. How is that? Let us show this using an example first, and then I'll give you more general results. So let us take the same XOR problem, which was giving problem with the perceptron, right? So now we will show that if we can solve the XOR problem if you add one more hidden layer to the perceptron. So that this kind of three-layer network now, let us define a small three-layer network just for this problem, like this. So there are two inputs, X1 and X2, then one hidden layer which has only two neurons. So output of these two hidden neurons, let's call them V1 and V2. And the outputs of these two neurons feed into the final layer output neuron. There's only one output neuron. So notation is like this, V1 is equal to G of X1 plus X2 minus 0.5. V2 is G of X1 plus X2 minus 1.5. So just like in case of McClelland-Pitts neuron, initially for AND gate or gate, we just by inspection, we just set the weights to make it behave like OR gate, AND gate, and all. Similarly, here also we'll just set the weights by inspection by intelligently analyzing the network and show that the network now behaves like the XOR gate. So V1 is designed to behave like the OR gate. V2 is made to behave like the AND gate, right? And then you combine V1 and V2 in the output neuron like this. V1 minus V2 minus 0.5. This will give you XOR gate. Let's see how it works. So V1 is this, right? X1 plus X2 minus 0.5, G of this argument. So which means the decision boundary between 1 and minus 1 is somewhere here. So that line is given by X1 plus X2 minus 0.5. So in case of V2, the decision boundary is given by this argument equal to 0. That's X1 plus X2 minus 1.5 is equal to 0. That gives you a line which is slightly more elevated. Now we want V1 minus V2. Okay, so how do you get that? That means, so imagine this function is 1 in this whole region and 0 in this whole region. This function is 1 in this whole region, 0 here, entire region. If you do this minus this, you see that you'll see that in this part, right, there is this part where this function is 1, this function is 0. So that remains. In this part, both functions are 1, so therefore they cancel out. So you will have a central region where there is a strip where the output is 1, and on both sides, on the flanks, you will find huge semi-infinite regions where the value is 0. Okay, so if you just take the difference V1 minus V2, you get something like this. Now just subtract some small positive number, like let's say 0.5 from this. Then what you'll have is the y1 equal to 1 part becomes plus 0.5. Well, like in y equal to 1 part becomes plus 0.5. Y equal to 0 regions will become minus 0.5. So you'll get three regions. Now pass this whole function right through the step function again, y equal to g of this whole thing. Then here you get 0, here you get 1, here you get 0. You get XOR gate. Okay, so we can show that this network is able to implement XOR gate. So what if you took only a perceptron, it could not learn XOR gate. But if you took a MLP with a hidden layer, you can make it behave like an XOR gate. Okay, so that's like only a proof of concept. That's not really a general theorem or anything which can show that it can learn arbitrary functions. So general results came a bit later. So in the 1888, there were a series of mathematical results that showed that a network like this, given enough number of hidden neurons, they can approximate or learn a wide variety of problems. So basically, these theorems go something like this. An MLP with a single hidden layer can approximate any continuous input-output function with arbitrary accuracy over a finite input domain, given enough number of nodes in the hidden layer. Now, this kind of results come from a branch of mathematics called approximation theory. So basically, in this class of theorems, what they do is you try to express an unknown function as a linear sum of a family of functions, and then you say what kind of unknown functions can this family of functions represent or approximate, closely. So this kind of results we've actually seen even in your high school or undergrad mathematics, but only thing is you don't call it a neural network, but it's a very familiar result. Take, for example, Fourier series, right? You can express any periodic signal as an infinite sum of cosines and sinusoids, right? You know that. Now, if you want the approx, so if you have all infinite terms, it will be perfectly accurate, perfect fit to the periodic function. But suppose you want to compute a periodic function in a computer, then obviously you can't have infinite terms. You can only have finite number of terms. So at what point will you truncate this infinite series? That depends on the accuracy you want. If you want accuracy of 0.1 or something, you might use only 3-4 terms. But if you want accuracy of 0.001, you might want to use some 50 terms. I'm just saying. Right? So depending upon accuracy, you'll have to have more or less terms. Here, logic is very similar, even in case of a neural network. If you want high accuracy, you want to have a lot of neurons in the hidden layer. If you want lower accuracy, you can manage with fewer hidden neurons. But the logic is very similar. Okay, so now the theorem basically says that the network can, in principle, learn and represent a large family of unknown functions, but it doesn't tell you how to get those weights. It says in the weight space there exist some weights which will make the network fit the unknown function very accurately, but doesn't tell you how to find those weights. So for that, you need training. So how do you train the weights? Again, it's the same thing, right? It's just exactly the same framework that we used to train a single neuron here. Right, exactly what we use for single neuron. We use the same thing here for a multi-layer perceptron also. So here you have multi-layer perceptron MLP. Input is X, output is Y. Compare with some target output. If the two are same, there's error is 0, then no change to the network. If two are different, error is non-zero, then network weights are all updated. So how do you update the weights? So for that, we again take an output error, EP, which is given as EI square. So EI is basically DI minus YI, squared output error. So you calculate that and differentiate it. It's a bit of math, it takes some time, but you can derive the learning rules. So this algorithm was discovered by 2-3 groups independently sometime in the middle of the 80s. So what they have done is they just didn't differentiate this and give the result. They introduced some new terms which they call deltas. Because what happens is at the output layer, you have an error that is defined. That is, at the output layer, there's a target value, which is DI, desired value, and the actual value YI. So error is given by DI minus YI. At the hidden layer, there is no such error, right? So how do you get error in the hidden layer? So for that, they introduce a new term called deltas. It takes a lot of time to explain this. I think it's also beyond the scope of this workshop. So I'll skim over this. So they define these deltas and then derive these learning rules. So once you have these deltas, what happens is the update for the weight is very similar to what we got in case of perceptron. For every weight, you'll have a delta at the top and a state variable in the bottom. Okay, so in this case, for this weight, for example, the delta at the top is delta AS, the state in the bottom is Vj, then weight itself is Wij. Then update for Wij is given as uh, equal to delta times x or delta times Vj. Okay, so the just like in the case of perceptron learning rule, the weight update is given as a proportionality as a factor of a product of the delta at the top and x at the bottom. Right here also exactly the same thing. Delta at the top times x at the bottom. The product of these two gives you the update for weights. So so to summarize this, we have derived this only for a single hidden layer network, but the same thing is valid for any number of hidden layers. So basically, training proceeds in has two phases or two passes. So in the first pass, you present the input, and that input then goes through all the hidden layers, goes to the output, and you get the output of the network Y. This pass is called the forward pass. Then you look at the difference between target minus Y or D minus Y. You get what is called delta. Then you back propagate this delta through these layers, through all the hidden layers, all the way to the first hidden layer. If you have only one hidden layer, then there's only one hidden layer. You back propagate it there. And for all those hidden layers, you calculate this new delta variables. So once you have all the deltas, right, for every connection, then you have a delta at the top and a Vj or a state variable at the bottom. The weight update Wij, delta W is simply proportional to the product of the delta at the top and Vj at the bottom. Okay, so in product is there's a multiplication factor, which is eta, the learning rate. So the expression for a weight update is eta times delta A times Vj. So this algorithm is called backpropagation algorithm, and it will work for any number of hidden layers. In fact, it will work for even much larger class of what are called feed-forward networks, right? So the example I've begun with is a network with only one hidden layer like this. But it will work, the same algorithm will work for a network with any number of hidden layers. Especially if you look at these modern deep networks, right, hidden layer numbers run into hundreds of hidden layers and all. So it's same algorithm works for them also. And not only that, you can look at even much larger classes of topology. So where look at this example in the top, right? There's some feed-forward layers, and then here the weights are jumping on top of this, and here input is coming straight away into some hidden layer, bang in the middle. Here input is going straight away to the output layer, and all sorts of things are happening. Right? The only thing about this network is there are no loops anywhere. All connections go in only one direction. That means if you follow these arrows, you cannot start from a point and come back to the same point. It will never happen. Yeah, so therefore, all these networks are called feed-forward neural networks. This backpropagation learning algorithm will apply to this entire class of feed-forward networks. So it's a very general network. So it's a very powerful class of networks. You can train very hard problems, and so you just have to have. You don't have to analyze the problem and see how it works. You just have to have examples from the problem. You can train network on that. The disadvantage is that it's like works like a black box, and it doesn't. We don't understand how it works, and so on and so forth. But all these are problems in the early days of these networks. Now we don't care as long as the networks gives good performance and able to generalize well to the training set. I'll skip some of this stuff. So when you train the network, so usually the training by itself with the standard backdrop, it's a bit slow. So there are various ways of accelerating backdrop. There's something called adaptive learning rate. So usually learning rate decides how fast the learning proceeds. So that's the eta. But thing is, if you make eta very big, then the network may not converge, right? And it will start oscillating as it approaches the minimum point. So what people do generally is start with a large eta initially, and as training proceeds, as you approach solution, decrease eta. Then there's a term called momentum, which will also give you similar kind of acceleration. There are also higher order methods where the weight update depends not just on the gradient, that is first derivative of the error function, but also uses second derivative. So these kind of algorithms take much more memory because you have to maintain the entire the Jacobian, right, and also look at the Hessian for the second derivative, but they can converge in fewer steps. Okay, then when it comes to stopping the training, when do you stop training? A simple way to answer that is you have a separate validation set and the training data set. As you keep training the network on training data set, error keeps going down normally. But when you train it too much, the validation data performance start going up, which means it is now not generalizing well from training set to the validation set. So you stop at that point where the performance on the validation set keeps going up. So that kind of stopping is called early stopping. Okay, yeah.
Can you repeat that, sir?
Yeah, so basically to decide when to stop training, you have to have two data sets, the training data set and a separate validation data set. So what you do is after every epoch of training, you keep plotting the performance of the network, the error of the network on both the training set and the test set or validation set. So what will typically happen is the performance of network on training set will keep going down. Especially if the network is a big network, it will keep going down. But the performance on the test set will start going up after some time. Because after a point, the network will start overfitting. It doesn't generalize well from training set to test set. So that's when you have to stop training. Don't train it any further. This criteria for stopping training is called early stopping.
So you stop when the testing dataset performs well.
Performance, no, tested performance starts getting worse.
Oh,
This is error curve. It's not accuracy. It's error.
yes, yes, sir. Now I understand.
Training error, it doesn't tell you this. If you look at training error alone, because it keeps improving. But that's bad because just like when you study for exams, there are two approaches to study. One is simply mug up all the example problems and their answers and everything. The other approach is to understand the concept and then learn to solve new problems with the help of the concept. Okay, obviously, the second method is better. So let me illustrate that using a Venn diagram. So basically, what the network is doing is it is trying to learn an unknown function by using a bunch of samples drawn from that function. Okay, so illustrate that in set theoretic terms. Look at this plot. The outer rectangle is like the set of all. So if any function is basically a set of input-output pairs, right? It's defined by a bunch of input-output pairs. Now U is a universal set which consists of the whole universe of input-output pairs. Okay. In that, I want to learn one function. So that function is given by this ellipse here. That function defined by a bunch of input-output pairs. But that function will be typically some continuous function, so I cannot draw infinite number of sample data from that. So I'll take a finite set, and hopefully I would imagine that I assume that those points represent the set completely. And that's my training data set. That is just T here. Okay, and using that, I train the network. So if I train the network very well, the network will, let us assume that it will perfectly learn all the training data points. But it will also learn some other data points. So once it learns the data points of the training set, it is done. Because then the training algorithm has no way to decide what other things it will learn, right, in the process. So what the network learns could be something like this slanted rectangle. Okay, so this slanted rectangle completely includes the training data points, T, but also includes a bunch of other points which is outside T. That's can't help it. Now, if you can think of certain training data, test data set X, which is completely outside the purview of the network. Right? This is just given deliberately just to show the problem. So in this case, if you give X to the network, it will perform badly in all the test data set. Okay, so because network has generalized in a totally weird direction, right? This is in principle possible, I'm saying, right? So therefore, what you have to do is have a separate test data set and keep checking the performance on the test data set, and make sure that the performance on that is also fairly good. If that is getting worse, then you stop training. The same thing can be illustrated in a slightly different graphical form like this. Suppose my training function or a unknown function, target function, is a parabola which is given by this y equal to 4x into 1 minus x. It looks like inverted, like an inverted bell curve. Now, if I take some data points from this and assume there's some noise in the data and take a large network and train it to death, right? Imagine it will go perfectly through all the data points and it will give a fit like this. Its training error is 0. Okay, but with all these wiggles, you see that it's not able to capture the underlying parabola unknown function. So now if you give this kind of a network to a different training data points, it will perform badly in all of them. Okay, so whereas an ideal fit would be ignore the noise, try to get at the underlying pattern, right, of the function, right? And if you do that, then you should be able to recover this parabola. So these arguments are easy to make in case of simple examples. They also use theory like VC dimension and all that to decide this generalization issues. The main problem that you need to address here is how do you match the network complexity with problem complexity? Network should not be, the number of free parameters in network should be optimal. Not too high, not too low. If it is too low, then training error itself will be very high. If it is too high, training error will be low, but test error will be high, right? So it should be optimal, right? So for that, people do a lot of things to improve that generalization. So since the number of weights, the number of free parameters should be optimal, what people do is you add separate mechanisms for weight decay, so that only the most important weights will survive, the rest will just simply attenuate and die. So you'll typically have some kind of a weight decay term. So in the cost function, the output error function itself, you have a separate cost term for that penalizes large weights. So the objective now is to get low error while using minimal number of weights. Right. So how do you do that? Have a separate cost for weights and penalize it for large weights. So that cost can be something like sigma wi square. And when you differentiate this to derive the backlog learning rule, then you'll have something in addition to the eta delta v term. You'll have some kind of a minus wi term that will penalize large weights. There are also more sophisticated methods, like for example, something called optimal brain damage. So where you figure out the contribution of every weight to the output error. And so suppose you set a weight to 0. What is the change in the output error? If it is not much, then that weight is not very useful. So just remove it. In fact, even with very, very early studies on CNN, so convolutional networks, people found that trained on MNIST data, people found that you can get rid of large number of weights and still have pretty much the same performance. In fact, that kind of a lean networks will generalize well to the test data sets. Okay, so this kind of a weight pruning is even weight whatever reduction is called pruning, and this is done to improve test performance, improve generalization. Let's take a short pause. Any questions?
Sir, good morning, sir.
Yeah, please go ahead.
Sir, what's the main function of a bias, sir?
Of a bias?
Yes, sir, bias.
Okay, so we can give the answer in biological terms and mathematical terms. In biological terms, because the neuron is supposed to imitate the neuron model is supposed to imitate the real neuron. And if you look at what we got from Hodgkin-Huxley model, there is an output firing rate response only when the input current is more than some threshold. Okay, so this curve here, right? So to capture that in the neuron model, artificial neuron model, also you need to have some kind of a bias. Otherwise, it will start firing right from the point when the current becomes positive. Okay, that is a biological answer.
Okay, sir.
The mathematical answer is, which is more important when you are doing computation modeling. So the theorem here from Sebenko says that only an expression of this kind. Okay, so say this is just an expression of the neural network with one hidden layer. It's a linear sum of a bunch of these G functions. The argument of a G function will have sigma wij xj minus b. This is a bias term. So the theorem says only an expression of this kind will be able to approximate any continuous input-output function with arbitrary accuracy. So theorem says I need that term. Okay, without that, the theorem is not valid. So that is a mathematical justification to the bias.
Okay, sir.
Is-
Thank you, sir.
So I'll give one more example. Take Taylor series,
Yes, sir.
right? You can express any unknown function as a Taylor series around a small neighborhood of a given point. What is Taylor series? You have a0 plus a1x plus a2x square, all that, right? You all know this. Now think of the first constant term as a bias term, and I'll remove that. Now is the Taylor series valid? It's not valid, right? That's the mathematical result. You need to have that constant term, otherwise the expansion is not valid. So like that, the mathematically also you need that bias term. So both biology and math, they coincide, they converge, and giving you the same result. Hope that is satisfactory.
Yes, sir.
Okay, so yeah, any other questions?
Good morning, sir.
Yeah,
So, if you are mapping a disease condition, whether both weight and bias both will change?
no, when I talk about disease, that's a whole different story. Because let's say something like stroke,
Okay.
right? In stroke, because of loss of blood supply, certain part of the brain tissue is damaged. That means both neurons and the corresponding weights will be destroyed.
Oh,
So how do you do that? In the network, you have to remove some weights and neurons. In fact,
okay.
after my talk, Sundari will be talking about exactly one such model.
Okay, sir. Thank you.
You basically have to remove the neurons and or weight. We typically remove neurons, whole neurons, to
Oh,
capture that.
okay, sir.
But
Okay,
if you are looking at a disease like, for example, multiple sclerosis, in
Okay.
multiple sclerosis, the problem is with the connections, not so much with the neurons. And not
Okay.
even that, the connections, the fibers, there's something called a myelin sheath. I didn't spend much time on that yesterday.
Okay.
That is, the fibers have a coating called myelin sheath. Because of this coating, the conduction velocity remains high. In multiple sclerosis, this coating, that coating peels off literally. Because of that, the conduction velocities go down. So now in a computation model, how do you capture that? So you cannot capture that first of all in MLP because there's nothing like conduction velocity in a MLP connection because they're all static connections. So you need to have cables and then implement this reduced velocity. That's a bit more complicated. You cannot do it with an MLP.
Okay, sir.
Okay, so yeah, so now let us take this MLP and look at a few very old application. In fact, I don't know if you've heard of this book. In the 80s, when they proposed the multi-layer perceptron and backprop algorithm and all that, many other important models were also proposed. For example, the Hopfield model. Hopfield got a Nobel Prize last year for his work. His first paper was also published in 82 and 84. So 80s was a very crowded, very creative period. In fact, that period has resulted in what is now called the connectionist revolution. So that is this that line of work gave the idea that in the brain, the more important thing is the connections, not the neurons themselves, right? And it's information is all encoded in the connection. Connections are the key. They're the most important thing. So that's called connectionist revolution. And as in the wake of that kind of a revolution, a group of people they have started a conference series, and this conference and published a lot of papers, and then though they were all compiled into 2 volumes. It's called Parallel Distributed Processing, or the tagline is Explorations in the Microstructures of Cognition. A very beautiful expression. So they said, how does the brain do cognition? And exactly what happens at the level of the microscopic structure, the level of neurons. in the brain when we cognize something. The two volumes are titled as parallel distributed processing. So I'll take just a couple of examples from that just to illustrate how very simple learning models can explain a lot of cognitive phenomena. The first study I'll look at is what is called past tense learning. So with English, thing is learning past tense is slightly complicated because there's no single regular pattern. Okay, whereas Indian language I don't think we have that problem. So typically what happens is when children learn the language, when they learn the past tense forms of verbs, they face some difficulty at certain age. So because what happens is in case of past tense, there are simple verbs or commonly used verbs like come, get, and give, and all that. For them, so in case of past tense, there are certain verbs which have the standard ending. For look, it is looked. Okay, for need, it is needed, and so on and so forth. Whereas for some other verbs, that ed ending is not there. So come and came, and got is got, get and got, and give and gave, and so on and so forth. So you have regular ending, which is d or ed ending, and then all this words with irregular ending. So what happens is when children learn, they start with these very frequently used verbs. Most of them have irregular endings. Okay, then at some point in a stage 2, at a slightly later stage, they get exposed to all these lots of verbs which have regular ending like wipe and wiped and pull and pulled and so on. Then what they do is they discover this new rule that past tense means ending and adding a d or an ed. Then they incorrectly apply this to the words that they have learned in the first stage. And so therefore come becomes comed and or came and so on and so forth. They start making these mistakes. In stage 3, again, their vocabulary stock increases further. So then they sort out this problem and learn to use the proper ending for this commonly used irregular verbs, and also start using the correct ending or the regular ending for all the regular verbs. This happens at the third stage. So people have thought of this phenomenon for a long time and came with all sorts of rules and theories of how children learn or how they make all these mistakes. But with the advent of neural networks, they train a neural network on the same problem, and neural network also starts showing the same mistakes. Okay, so how did the training work? So they've taken a simple perceptronic, not even MLP, and they've taken a bunch of verbs. They've taken a set of 10 high-frequency verbs that is commonly used verbs like come, came, get, give, take, and all that. Then 410 medium-frequency verbs. Among them, 334 are regular and 76 are irregular. And then 86 low-frequency words. Among them, 72 are irregular and 14 are irregular. So in stage 1, the training network can only the high-frequency verbs, the first set, for only 10 epochs. This stage 1 is supposed to represent early stage learning of the children. Then in stage 2, they have taken the second data set with 410 medium frequency verbs, and they trained the same network further, right, beyond stage 1. In stage 3, they only tested the network on these 86 low frequency verbs, no further training. So let us see what happens. So the first 10 epochs is stage 1. So network has learned to perform well, both on regular verbs and irregular verbs. But after stage 1, when it entered stage 2, it is suddenly exposed to a large number of regular verbs, 334 regular verbs in this 410 medium frequency verbs. So the regular verbs with the ed ending started dominating the network's learning. Because of that, what happened is, the moment the network entered stage 2, it suddenly started making a lot of mistakes on irregular verbs. It was okay with regular verbs. It kept increasing its performance. But after a lot of training, then slowly the network started clearing this confusion, and it started performing well on both regular verbs and irregular verbs. It behaved exactly like how children, right, were making those mistakes. So these kind of networks gave a lot of insight into how people learn. Okay, one more example of this kind is our famous convolution neural network. The convolutional network was actually first proposed in the late 90s. It was proposed by a guy called LaCoon and done implemented at AT&T company. Its aim was to read the zip codes or pin codes on US postal envelopes. So the convolutional, so in NLP, you just have one-dimensional arrays of neurons, whereas as probably a lot of you know, in case of CNNs, you have 2D arrays of neurons because it is meant to recognize images. So the input is a 2D array where you give the image, and the hidden layers also up to a point are 2D arrays. So each hidden layer has multiple 2D arrays. These are called feature maps. And so in this case, for example, it was trained on the famous MNIST dataset. That was when the first the dataset was created. So input is 28 by 28 images. Then the first hidden layer, you have 4 arrays, each of size 24 by 24. Then after that, you have subsampling stage, where you have again 4 feature maps, but you divide the size to half in both dimensions. Then again, you have a convolution stage where you expand the number of convolutional feature maps, but reduce the size. So what happens is, as you go towards the output layer, the convolution layer sizes keeps going down, but the number of convolutional feature maps keeps going up. And again, we have alternate convolution subsampling stage. The whole trend that you're creating here is to go from this spatial 2D array to a linear 1D array. Okay, and you have to do it in gradually so that you destroy the spatial structure in stages, but keep the feature information. Okay, and feature information at lower levels, you have only small local scale features. And as you go higher and higher, you look at larger scale features. Okay, and each neuron in a convolutional layer receives input only from a small window of neurons in the previous stage. And that window is called the receptive field of the neuron. So as you can see that neurons in the lower layers have small receptive field, neurons in the higher layers have larger receptive fields. And neurons highest layers will have receptive field which covers entire input image, right? And finally, after a bunch of these convolutional layers, you'll have one-dimensional layers, which are called dense layers in more modern terminology. And you'll have a bunch of dense layers. Finally, you have the output layer where you classify the pattern. Okay, so this network was very successful even those days. It was trained on MNIST data, and after training the data, they tested it on all sorts of weird shapes like this. So I think LaCoon's website is still there. You can look at some of these examples which are called weirdos. So 2 is given like this, like a bunch of circles. 4 is given as a hollow 4. 6 is given like this with broken contour and so on. But it's able to recognize all of them very well, although it was not trained on those kinds of patterns. So see all these examples. So convolutional network itself is an improvement over an even older model called a neocognitron, which was proposed by a Japanese researcher called Fukushima, Kunihiko Fukushima. And that was in the 80s, and then LaCoon improved it further, simplified it further, and came up with this CNNs. Okay, so let us stop here, take a short pause, 11:12. So let us meet again at, let's say, 11:25, right? And then continue. So what I will do now next is, I take this kind of a deep network structure and apply this to brain and show how you can understand brain's anatomy, brain's organization very simply by thinking of it as some kind of a deep network. Okay, any questions?
Hello, sir.
Yes, sir.
Yeah.
Sir, in that past tense example, no,
Yeah.
like that difference happened because did the data had more examples of that regular words? That is why
Yeah.
the network also. So
Yes.
So all the, okay. So the difference happened just because the model was exposed more to one particular type
Yeah.
of example.
Yeah.
Okay.
So all that network did is it's simply a learning system.
Yes.
Right? There's nothing like there's no anatomy or anything. It's just a very general learning system. The real reason is that composition of the data set. That's all.
Thank you, sir. Yeah.
Yeah.
Hello, sir.
Yeah. Yes.
Yeah, sir. Thank you so much for the lecture. I just have one question.
Yeah.
Is that when you were talking about past tense learning and you were telling about the training, that how they trained the words, how they trained it, the model for the words. So I just wanted to understand the, like, a very basic overview. How do they train the
Yeah,
model?
it's actually a perception. So there is a convention called Wickel phone features. Okay, using that they could describe the word. So the input word is basically a bunch of characters, right? Output is the sound, the phonetic notation of that word, and further they use something called Wickel phone features. So that's also a vector. So it's a mapping from one vector to another vector.
Good morning, sir.
Yeah.
Sir, I just find it hard to intuitively understand the concept of overfitting. Can you just give some intuition about that so that I can understand?
Okay, let me go back to that. Let me share again. So you see this example. Okay, my target function I'm trying to learn is this parabola. Okay, given by this formula y equal to 4x into 1 minus x. Now, when I take training data from this, right, I just take a bunch of data points and assume there is also some noise. Okay, so these data points don't exactly lie on this curve. And let's say I take some 10 or 20 data points and train the network. Now, the objective of the network is the network should aim to get at the underlying curve without getting misled by all these noisy variations. But if you train the network very hard just to get zero error on the training data sets, then what will happen is it will go through every one of these data points perfectly, giving you an error of 0, but it is missing the underlying structure. Okay, especially this will happen if your network is very large, then it will go through every little wiggle in the data points and it will learn all of it. Now, if you give it a new data set, which will have again noise at the test set, and apply that to this network, right, then it will give poor result. Right, whereas a network which ignores this noisy variations and captures the underlying pattern of the function.
Pattern.
Yeah, so that will give you good result on both training set and test set. So how do you know that, right? That's where this early stopping helps. The whole point of the network is not just to get a low error on the training set. You should also get low error on the test set, right? So therefore, as you train the network, you not only look at training performance on the training data set, but also look at the performance of the network on a separate validation set, right? So you don't use the validation data for training, but use it for just to cross-check. If you're training too much on the training data set, then at some point the network will start performing badly on the validation set. That's when you should stop. Right? The way you study for exams is a great example. Like, I had a friend long ago. This guy would actually mug up, like, if you have some kind of lecture notes with a lot of worked out examples. He would literally memorize all the worked out examples. So he would like tell you what is the answer for which problem and all. That kind of approach will work well if the exam gives you questions exactly from the same question bank or something, right? But otherwise, you have to understand underlying concept and then learn to solve new problems based on the concept, not just mug up problems. So in case of overtraining, one way you can say it is mugging up problems, example problems, right? Instead of trying to get at the underlying concept.
So thank you, sir. It's very intuitive example, actually.
Okay, thank you.
Hello,
Any
sir.
other question? Yeah.
Yeah. Sir, will you explore adaptive learning rate? What is difference between adaptive learning rate? and learning rate?
So normally learning rate is a constant, a proportionality factor, right? But the problem with that is, say, think is if you use large learning rate just to get faster training, as you go, what is that? Somewhere I should have that.
Suppose you are
Yeah,
using Adam optimizer, okay?
yeah.
And and how you use adaptive learning rate?
Yeah, so look at this, for example, if so let's look at the trade-offs. If eta is very high, so here let's say you are very close to the minimum of the error landscape. If eta is high, then instead of going slowly towards the minimum, it will bounce off and it will diverge, right? Error will start going up again. If eta is too low, it will creep slowly towards the minimum. It take a very long time. So what people do is change eta based on. So thing is, suppose it's diverging. What happens is error. They'll see a lot of fluctuation in error, right? Which means when you see a lot of fluctuation in error, which means eta is too big. So reduce eta. If error is not fluctuating and going in the same direction very slowly, that means eta is too small. Therefore, increase eta. This is the kind of a logic of adaptive eta.
Okay.
They change eta based on the pattern of error change in the recent time steps.
Okay, sir.
Okay, any other questions?
No, sir.
Sir, why is there a analogy between CNNs and our visual network? That like the
Yeah, I
deep,
will
deep.
come to that in the next half.
Okay, okay.
Right, just give me. So let us take a short 10-minute break. Come back at 11:30 and then we'll continue. Thank you. All right. Okay, so just to continue. So what I'll do now is I'll present brain's organization by looking at brain as a deep network. And I want to show how simple brain looks when you see it from this deep network perspective, now that we understand what a network looks like and how it can be trained and so on. So I want to begin with this very beautiful book. If you have time, try to get hold of this PDF somewhere. It's called Vehicles, right, or Experiments in Synthetic Psychology, written by an anatomist called Breitenberg. He's a microanatomist. He's done excellent work on studying the microstructure of the brain. But he also written this delightful little book, a popular science book called Vehicles. Basically, he thinks of body as a vehicle and brain as a driver of that body. And the main recurrent idea in this book is you don't need very complex organizations to produce complex behavior. Even a simple organization, a simple brain with a simple organization, in its interaction with a complex environment, can produce complex behavior. So it's all in the environment. So just like in the past tense learning, we have seen that the change in the word composition has produced change in behavior. There's nothing to do with, intrinsically with the network itself. So like that, even a simple network in interaction with a complex world can produce complex behaviors. Okay, so if you look at it from that perspective, brain will actually start looking very simple. So he comes up with this artificial machines or imaginary machines, and then looks at their behavior. So these machines typically have some kind of a sensor in the front and some wheels. So in the simple version, there is only a single photoreceptor, a photosensor in the front, and there's only a single wheel. The photoreceptor is connected to the wheel, and if the intensity of the photoreceptor is high, it drives the wheel faster. So it's kind of proportional. So there is a light source somewhere in the front of the vehicle. So the photoreceptor picks up senses the light and then drives the wheel. So in this case, the behavior is very simple. Nothing great happens. So the vehicle simply goes straight towards light source and hits it. So nothing very great happens. Now imagine a machine or a vehicle which has like much more rectangular. This one is more like a straight line. Okay, here it's more rectangular, and there are two sensors in the front and two wheels in the back. Now the two sensors in the front, they connect to single wheels at the back. So you're looking at, let's look at two organizations. One is The sensor in the front left will connect to the wheel on the left. Sensor in the right connect to the wheel on the right. Okay, and that's one case. That is case A. In case B, the wires get crisscrossed. Okay, right sensor connects to left wheel and vice versa. Just 1 second, I'll come back and see. So you have two cases, right? In one case, the wires go to the same side. Other case, wires go to the other side. This is interesting because this kind of a crossover of wires does happen in the brain. So he's deliberately using that pattern to see what happens. And so in the left case, what happens is you see that when the light source is on the right, the sensor on the right picks up higher intensity than the sensor on the left. So it drives the right wheel faster. So when the right wheel turns faster than the left wheel, you see that the vehicle will veer off to the left, right? So it look as if it is scared of light. It's turning towards the left. So when you look at that behavior, you can interpret it as some kind of a cowardice, right? It's scared of light, so it is photophobic or something, so it's running away. All that is happening simply because of this very simple organization of this wiring pattern that connects the sensors to the wheels. Now let us look at the one on the right. In this case, the light is on the left, so left sensor picks up more signal, which drives the right wheel faster. So therefore, the vehicle turns to the left, which means it turns towards the light source. And as it gets closer and closer to the light source, the signal gets stronger and stronger in the sensor. So wheels also will start spinning faster and faster. So in this case, the vehicle will turn towards light source wherever it is and accelerate towards light source and ultimately bang into it. So its behavior, when you don't know what's happening inside, you just look at the behavior, it looks as if the vehicle hates light, as it hates it with an aggression, right, with a vengeance. So you can give some emotional coloring to the vehicle's behavior. Now look at again a very similar organization, but only thing is in this case, in the first case, the connection between the sensor and the wheel is as a positive proportionality. That is, if the sensor signal is stronger, the wheels also turn faster. Whereas suppose the connection is negative, it means that the sensor signal is stronger, the wheels are driven with a lower velocity. Okay, so then what happens is you can work out the logic. When you have wires going to the same side, then as it gets closer and closer to light source, the signal intensity increases, but the wheels slow down, right? So what will happen is in the first case, this case A, the vehicle goes towards the light source, and as it approaches the light source, it will slow down and finally stop. Okay, this vehicle looks as if it adores light, right? There's a quiet adoration. In case B, again, when you have this cross connections and a negative weightage, it will go towards light source from a distance, but when actually it gets closer, it will turn away and slow down. So then it looks as if it has a fickle and fanciful love, right? So it's such a simple machine with just two sensors and two wheels and two wires. All that we can play around with is whether it's the same side connection or crisscross connection or positive connection or negative connection. With a small number of variables, see how many different behaviors a machine is able to show. So this is what Breitenberg highlights in this book, just to show that when we study brain, we keep focusing on all the complex details of the anatomy and all. But that's actually misleading. Just look at the simple underlying principles, and brain looks very simple actually. So let us continue on those lines and try to look at brain. So if you look at the nervous system, then there are two parts to it. There's part of it, the brain, which is our nervous system, which is inside the the bony vault, the cranial vault, and the vertebral column, the huge mass of neurons. Right, the mass of neurons inside the cranial vault or the skull, that is the brain proper. And then the other mass of neurons called the spinal cord, which runs through the entire vertebral column. Then, so both of these things are very nicely protected inside this cage of bone, and they send out these wires, these nerves outside, which come out of this kind of a bony fortress, and they spread all over the body, and that is called the peripheral nervous system. Whatever is inside this bony fortress, that is called the central nervous system. That consists of brain and spinal cord. And within the central nervous system, you have all these different parts: cerebrum, cerebellum, brainstem, and so on and so forth. I'll skip all this. So our goal is to understand the logic of brain's network and try to explain why different parts are doing what they're doing. So to understand that, first of all, we need to reorganize brain. In the sense, we need to look at the brain's organization very differently, like a deep network. Otherwise, it's very confusing. See, for example, this is like a typical kind of a picture that you get from a medical textbook or a medical literature. So you see that in the frontal lobe, this part of the brain, it says it is involved in movement, intelligence, reasoning, and so on and so forth. Again, look at parietal lobe, which says again intelligence, reasoning, and so on. So if so many different parts are doing intelligence, reasoning, what is each thing doing? Right? So it's slightly vague. The way you just mug up all these things and write exams, but without understanding why it is like that. So to understand the problem that we face when we try to understand brain's organization is something like this poem. So I'll tell you a poem, right? I'll just say that in this poem that it has 4 lines, and the third word of the first line is A, the fourth word of the second line is in, and so on and so forth. I'll give you like many such clues, and finally you have to understand what the poem is. It's very confusing to understand. Like the poem happens to be this poem by William Blake. Okay. So we need to do some kind of a reordering to put brain in a proper order and looking at like a deep network, and then it looks very simple. So think of brain as a big deep network. So in deep network, you have input in the input layer and output from the output layer. Between the two, you have a bunch of hidden layers. Brain is also like that. The input is sensory input, output is a motor output. And between the two, you can have many hidden layers. So then what you can say is, right, so let's say there are some 5 hidden layers. And you can say the input layer is sensory. And what about first hidden, second hidden, and third hidden? You can say they are all kind of sensory layers, because they're all still closer to the sensory input than to the motor output. Similarly, the 4th and 5th hidden layers, they are closer to the output layer, which is a motor output. So I'll just call them motor layers, right? Which is logical. Now, when it comes to brain, we don't have some general sensory input. We have multiple different kinds of sensors or senses. So you have auditory input coming from the ears, and visual input coming from the eyes, and touch input coming from the skin. So all these things, different kinds of sensory inputs are like different parts of the input layer. You can have to split this purple layer into multiple subsections. All of them feed into the hidden layers. Similarly, the output layer also, it's not just one big motor output layer. That also has to be split into multiple sections, right? Where different parts control different parts of the body. So one part controls eyes, that means eye movements. Another part controls hands, another part controls legs and speech, and so on and so forth. Okay, so this is like let's now progressively expand this. Now skip all this. Okay, so brain is divided into, there's a sheet of neurons that covers the entire brain surface. It's called the cortex. Inside that you have 6 layers of neurons. And then, so that covers entire brain surface. Deep inside the brain, again, you have lots of different masses of neurons. These are all called subcortical structure, because subcortex means below the cortex or inside the cortex. Now, the brain's outer surface itself is divided into these lobes. You have the frontal lobe here shown in the red, right? And the huge thing, and the yellow thing is temporal lobe. The blue thing is parietal lobe, and this bluish green one in the back is occipital lobe. This brown structure is the cerebral lobe. Now, there are some important landmarks which divide these lobes. Like, for example, there is one landmark called the Sylvian fissure, like this, running at an angle. another big landmark running vertically, that's called the central sulcus. You can see all that here. The central sulcus here, which divides the brain into front and back regions. The front is called is anterior and back is posterior. A big thumb rule is the posterior is all input processing, anterior is all output processing. A very big thumb rule. Now the sensory input from skin, like let's say you have sensory receptors in the hand, that comes into the spinal cord first and goes to the brain, goes to a specific part of the cortex. That's called the somatosensory cortex or the touch cortex, which is shown like this. Like I said, this central marker is the central sulcus. Behind it, you have input processing, and in the front, you have output processing. Okay, so this purple region here is the area where touch input comes to the brain, to the cortex. And here again, different. So if you touch, for example, my right hand, that will activate one part of it. If you touch my right foot, it will activate a different part of it, and so on. So there's a mapping of the entire body surface onto the brain surface inside this somatosensory cortex. Similarly, if you look at visual input comes from the world into the eyes, and from there it goes to a central part called thalamus. You can see here, and after that it goes on to the brain, to the occipital lobe, right? And that is here called primary visual cortex. After that, it splits into two pathways. One path goes upwards, this is called the dorsal pathway. Another path goes downward, which is called the ventral pathway. Now, if you look at auditory system, the sound input comes to the ears, and from there it goes through a bunch of layers. Then finally it goes to the cortex, which is called a primary auditory cortex, or A1. So you see that the pattern is same in all three. In case of touch, the touch information goes through a bunch of layers and finally goes to the primary somatosensory cortex, which is this purple region. And visual information also goes from the eyes over a long trajectory and finally reaches the primary visual cortex, which is in the occipital lobe here. And auditory information also from the ears, it goes through a bunch of layers and finally reaches the primary auditory cortex, which is here. So the touch comes here, vision comes here, and sound comes here. This is the primary auditory and primary sensory cortices are like this. Then olfaction is different. It goes from nose to olfactory bulb to different cortical areas, not shown in this picture. Okay. Now you see that some of the sensory pathways begin to blend and combine in next hidden layers. So because you have input coming from three different sensory sources, they all come to certain common hidden layers, right? Why is that? Because the sensory informations are not processed independently. They have to be combined, right? Suppose you look at a cricket ball, right? Cricket ball is red in color and hard to feel, right? So red in color, that comes from visual input. Hard to feel, that comes from touch, input. And if you tap on it, it makes a peculiar, like a tuck sound. That comes from the auditory, input. So you have to combine, how it looks, how it feels, how it sounds, all of that to construct a concept of the cricket ball. Right, so you have to combine all these different sources, and that combination has to happen in some kind of a hidden layer. And that hidden layer in the brain happens to be this somewhere here, the parietal. Why is that? I'll show you a picture later. Yeah. So you see that, let me get a better picture. Yeah. So touch is here, and sound is here, and vision is here. All of them actually, after this initial primary processing, the next stage comes to somewhere here. They all meet here. That's like your higher hidden layer on the sensory side. Okay, so that is this region. Right, you have to combine them because you have to come up with this integrated concept of various objects. So that is your parietal lobe. And within the parietal lobe, there are again subregions. In the posterior parietal cortex, which is somewhere here, you see that this part of the parietal cortex is midway between visual processing and touch processing. Right, and also So actually, if you look at this lower region, it's midway between sound, vision, and touch. So therefore, it combines somatosensory, visual, and auditory, and extract this higher level abstract information about the object. Where superior parietal lobule is somewhere here. This is between touch and vision. So it integrates touch and vision. Okay, and now there is this huge area called Wernicke's area. So when you look at language processing, ultimately language also has to come from the same sensory channel. Because how do you get language input? Could be reading something. That comes through the eyes and goes to the occipital lobe vision and then goes higher up. Or you could be listening to some podcast or something, right, or a lecture. Then that has to come through the ears, go to the auditory cortex, and then go higher up. The higher up is here, this common area, right? And or if somebody is blind, they could be feeling with their fingers and read some braille text, and that comes to the somatosensory area here and then goes higher up here. So all these things meet in this common area, which is like your slightly higher hidden layer, to which all these sensory inputs feed. And that's where language is comprehended. So that's called Wernicke's area. Similarly, on the output side also, we'll come to output processing later. Right, Wernicke's area is in the left posterior parietal, which processes language. Now, similarly, on the right side in the same posterior parietal area, it doesn't process language, but it processes spatial analysis, large-scale spatial organization of the input. And therefore, when there's damage to right posterior parietal area, the patients exhibit very strange kind of a behavior. They completely neglect the left part of the visual field, because what happens is in the brain, the right part of the world is processed by the left brain and that part of the world is processed by the right brain. So when there's damage to the right posterior parietal area, that subject will ignore the left part of the world in very strange ways. Suppose this was an example where the patient was asked to draw a clock. Just copy a picture of a clock. See that that person has mostly left out the details on the left side of the clock. They only have drawn the numbers on the right side. Okay, similarly, if you ask them to perform a visual search task, right, see that they're mostly confined themselves to the image on the right side. They're not searching the left side of the image at all. They kind of completely neglect that part of the image. Okay, so then if you go to temporal lobe, it has again, this is temporal lobe. And here we divide into three sections: superior, middle, and inferior. Superior means above, middle is middle, inferior means below. Okay, so this lower portion represents visual stimulus, visual object information. The middle portion looks at language and semantics and all that. The upper one process sounds, as we have already seen. Okay, all this is on the sensory side. Now let's go to the motor side. The motor layer in the final output layer has, like I said, you have separate areas for hands and legs and all that. Now, if you go slightly backwards, you will have hidden layers from where you control all the different outputs, right? So that is in the so the output layer itself is like this part. Okay, and the hidden layer, which is behind the output, that is this hidden layer, is like these regions. Okay, so that's called the frontal lobe, and within that you have the primary motor cortex is like the final output layer. After that, it goes to spinal cord and then goes to the muscles, producing movement. But before that, you have premotor cortex, right? And then even before that, you have supplementary motor cortex. So imagine you have more hidden layers here. This is like primary motor cortex, and one before here is like premotor, and one before that is supplementary, and so on. Okay, and so I'll skip some of this. So like that, you have layers close to the motor output layer. These are all higher order motor control regions. Then layers close to the sensory layers. These are all higher order sensory representation layers. And between these two extremes, you'll have central layers. And what are the central layers doing? So the one close to the input is sensory, one close to the motor is motor. So what is central layers doing? This is where we have to expand the picture of brain that we have seen so far. It's not simply like a feed-forward network. There has to be some kind of a decision making that occurs in the center. Otherwise, whatever input we get, we directly explicit and produce output, which doesn't make any sense if you think about it more logically. We are not just stimulus response machines, right? For example, if I give you a toothbrush right now, you won't pick it up and start brushing yourself. It doesn't make any sense. This is not the time for brushing your teeth. Similarly, if I give you a hammer, you don't start, automatically hammering nails on the walls. So there's no need for it. There's no context. So just because an input is presented to you, doesn't mean you immediately produce a relevant output, right? Because it may not be necessary, it may not be relevant, may not be timely. So therefore, whatever input is given to the network, it won't automatically produce the output. There has to be some kind of a gating that occurs somewhere in the middle that decides which action should I exactly produce, and should I actually perform an action or not, or remain silent. Okay, so some kind of decision making has to occur somewhere in the middle, right? Otherwise, we'll be like completely slaves of the environment. In fact, there is certain brain conditions, psychological conditions, where because of damage to the prefrontal areas and basal ganglia and all, people simply behave like this. They become completely slaves of environment. There's no decision making. There's no control at all. And where does the decision making occur? Exactly in the middle, right? That's where all this information comes. You have highest level representations, and somewhere here you have to decide, okay, should I go with it or not? And that central part in this network is like your prefrontal cortex, which is here, and there are several areas here, and one part, right? Okay, we'll skip some of these things, but point I'm trying to make is, look, in the deep network picture, I just had inputs in one end and outputs at the other end, right? And there's a continuous linear flow of information from left to the right, right? But that's not how it occurs in the brain. The input from the senses come, right? If you look at visual information, it comes at this corner, and the sound comes in this region. Touch comes to this region. Okay, that is just like purple boxes in the deep network. Where does it go next? The first hidden layer or a bunch of hidden layers. Where are these hidden layers in the brain? Here. Okay, and after that, where is the centralmost layers? That is, you have to jump all the way to other end of the brain. You have to go here. Right? After that, then you go to motor areas. So you have to go here. From here, you jump here. So point is, so start here, jump to this central part. From here, jump to this end, then jump to this end, then you go out. So brain is indeed like a deep network. Only thing is it's folded in some very weird ways. If you unfold it, then it looks very simple. Logic is very simple. Okay, so with this, I will stop. And so all the decision making occurs in the prefrontal cortex. I'll skip some of these things. But with this picture setup, I think it's quite easy to understand brain in terms of a deep network. And tomorrow I'll elaborate this further. And because right now I've given a very static picture of the brain. It's a deep network, yes, but it's not a static deep network. There is dynamics in it. So how dynamics occurs, that I'll describe tomorrow. But today, I think with this picture, next Sundar is going to talk about how you can take a CNN and biologically constrain it to represent the two hemispheres of the brain. And with that, you can understand a lot of things about stroke, right? So I'll stop here. Any questions from anybody?
Yeah, hello, sir.
Yeah.
Yeah, thank you for the wonderful lecture, sir. I have one question, like regarding the last part. It's general as well. We have various secretions in our body, right? So, like what to say, in our body there are RBCs, WBCs, etc.,
Blood.
etc.
Yeah.
Yeah, I'm talking about generally. I don't know how to give an example. That's why I'm asking like this. I'm curious, like what controls this dosage or amount in the blood, or like the heart or whatever? Is it the brain or the organ itself?
No, I don't know about the blood because you're talking about immune system.
Okay.
But if you look at heart, for example, heart is a semi-autonomous organ. Okay, left to itself, it will keep on beating at some rate.
Oh, okay.
At a fixed rate. Even if you can actually take an animal heart out and then put it in some bath which has the nutrients, it will keep beating by itself.
Okay.
Okay, but it will beat at a fixed rate. That's not sufficient because Suppose you are lying down quietly, then you don't need much energy. But if you are jogging or sprinting, you need a lot more energy. So rate has to go up. Right. So that cannot happen if you leave heart to itself. That has to come from brain's control.
No.
So the sympathetic system will activate the brain and then it will speed up.
Okay.
Or if you are taking rest, then the sympathetic slows down, parasympathetic picks up, and that will slow down the heart. So the kind of
So the
adaptive dynamic control of the heart comes from the nervous system. Although it has its own intrinsically some level of autonomy is there, this kind of modulation occurs because of brain's input. Same thing with respiration, same thing with gut function, always. There's an intrinsic function, but modulation coming from top. It's like state government and central government. A lot of things state government can do on its own, but certain things are under central control.
Yeah. Yes, sir. Thank you.
Yeah. Any other questions? Basically, what I want to drive at in this segment of the talk is brain looks all confusing, but if you unpack it and put the various brain regions in the correct order, it's just like a deep network, right? Multiple inputs, multiple outputs, a lot of hidden layers, and there's a decision-making part in the center. That's all. So that picture itself will carry you very far. You can understand a lot of things with this simple picture. Then we'll add dynamics to this tomorrow. Okay, any further questions? Yeah, somebody is saying there's beautiful order in chaos. Yeah, chaos, it's chaos only if you don't understand the order, the logic of it. If you unpack it, it's very simple. Okay, any other questions? Otherwise, I'll leave and let Sundari take over. Sundari, are you? So will it?
Yes, I'm here.
Yeah, I think yeah, unshared. You can get started.
Okay, sir.
Thank you, guys. See you later.
Thank you, sir.
You can also send me mail if you have further questions. You can always send me mail. All right. Yeah.
Hi, good afternoon. Can you guys see my screen?
Yes, ma'am.
Okay. Okay, so I think let's get started. So my name is Sundari. I'm a PhD student at the CNS lab. And today I'll be talking a little bit about my thesis work, which deals with using deep networks to understand motor function, both in normal and under motor stroke, specifically dealing with upper extremity, that is the arm. So here we will be looking at how CNNs, the convolutional neural networks, can be used. And this is the basic layout of today's session. First, I'll start with a small brief introduction about what stroke is, how is it usually managed and treated, and the current problems in the state of the art. And we will from there move on to how computational neuroscience can help in solving these problems. And then I will give a system overview and a description of the computational neuroscience system that is going to be used to solve the stated problem. And then we move to the methods, results, conclusion, and the future directions of such a system. If you guys have any doubts during the session itself, please feel free to pause me and ask me. I might not be looking at the chat, but you can unmute yourself and ask me the question. So first, a brief introduction of what is a stroke. A healthy person can be affected with a stroke due to either a blockage or a rupture in one of the blood vessels supplying to a part of the brain. The result of this is the neurons which were previously supplied by that blood vessel die. Because of this, the functionality that was governed by those cells are lost, and the most common issue that is left over after a stroke is a disability. And this is most commonly manifested in the upper extremity. This is mostly due to the organization of the brain and the physical features of the blood vessels, which makes the blood vessels that supply mostly to the motor cortical area in the brain, more weaker and hence more capable of undergoing a stroke than any other blood vessel. Now, the treatment that is administered to overcome this disability is physical therapy. And after many rounds of physical therapy, the patient regains functionality. However, this regaining of functionality is only partial in nature. Although this situation or this picture seems very straightforward, it gets very complicated because of the treatment that is administered, that is the physical therapy. This is because physical therapy can be of many different forms, and there is no clear identification of understanding of when a particular therapy needs to be administered to a patient, or why a particular therapy works for a given patient versus why it does not work for another patient with almost similar lesion or stroke characteristics. A most popular therapy that is administered is called as CIMT, or constraint induced movement therapy, where the healthy arm is constrained by using a glove or an oven mitt as shown in the picture here, and the affected arm is made to perform multiple different tasks, from gross movement tasks like spreading butter on bread or pouring water into a glass, into fine motor tasks like separating beads into different categories, etc. Another therapy that is used is the bimanual therapy, where the healthy and the affected arm are both moved in tandem with each other. As you can see from just the administration of these two therapies are very contradictory in nature. The other most popular therapy is the mirror-based therapy, where the affected arm is placed inside a mirror box and the unaffected arm is placed outside it. Now, the patients are encouraged to move their unaffected arm, but because of the mirror box placed here, it creates the illusion that their affected arm is the one that is making the movement. This creates an illusion in them that their affected arm has recovered, and thereby sets up a positive reinforcement loop within them, giving them more confidence to start using their affected arm. Now, there are multiple other therapies similar to this, but I'm not going to be covering all of it. But the thing that you should notice here is that all of these therapies can be grouped under something called as a task-based rehabilitation. What I mean by a task-based rehabilitation is, in all of these therapy types, a particular set of tasks are given to the individuals, and they are made to repeat the task over and over again under any one of these modalities, and they are made to repeat them until they get better at performing that task. This creates a problem here. Now, just like Sir had talked about overfitting and mugging up and rote learning, etc., what happens is the patient might get very, very good at performing these tasks, but might not become or might not generalize to other tasks that they require for everyday life. This makes them not really regain functionality as a whole. In order to combat this, scientists have or researchers have come up with a different kind of therapy called as the exploratory rehabilitation, or playful movements, where the patients are encouraged to explore the workspace that is provided to them and make any type of movement that they would like. That is playful movements. With this, what researchers have found is, because the patients are encouraged to make the movement that they want, that is, it's more voluntary in nature, the recovery set up by this type of rehabilitation will be more than what is seen as task-based rehabilitation. So with all of this in mind, again, we see that there are multiple different treatment options available to a patient, and multiple different theories of what works and what doesn't work. But there is no introduction of patient characteristics in any of this. Like, if suppose a patient is administered for or admitted for any other kind of problem, like a fracture or a fever, etc., the mode of treatment is different based on what the affliction is. But here, although the mode of treatment is different, there is no actual correlation with the patient characteristics itself. This is one major problem here in physical therapy that is used for stroke rehab. This is one of the reasons for a computational model. The other reasons are, now let's say you know the place where the lesion, that is the stroke, has occurred and the size of the lesion using imaging techniques. But you have no idea what the impairments are going to be. A computational tool will be able to predict the impairment even before the patient is stabilized and can be discharged from the ICU. The other is, once the impairment is predicted, we can simulate different types of therapy, as I have shown here, and see which of these is going to be the most optimal one to give recovery to them, and also see the trajectory of this recovery under different rehab paradigms. Once this is done, we can also find the optimal rehabilitation protocol, that is, which therapy is to be used, at what time, and how much. This eliminates a trial and error way of finding the rehabilitation protocol. Now, the reason why this is extremely important is because as soon as a subject is afflicted with stroke, there is a small period of time where the plasticity, that is, the ability of the neurons to recover, is extremely high in the patient. And hence, the treatment is very highly time sensitive. That is, we need to start administering the treatment as quickly as possible in order to make sure that the recovery is as good as we can hope for. Therefore, we cannot use a trial and error way of looking at the rehabilitation protocol, and we need to have an optimal rehabilitation protocol already found as soon as the patient is out of the ICU. Now, this is the high-level overview of the system that we're going to be using. We're going to be using a convolutional neural network model, to which we get inputs as the left and right retinal images of a target that is present in 3D space. Now, the goal of the model is to understand the location of the input, that is the target, in 3D space, and provide the muscle activations that are going to be necessary to reach to that target from a given rest position of the arms. Now, the reason why this is how it's designed is because this is very realistic to what happens in the brain. That is, the eyes receive images of the target in the visual workspace and then communicate it through the visual hierarchy and then to the motor hierarchy in order to compute the activations that are going to be necessary for the arm to reach to the target. Now, by introducing damage to this network, we can start simulating characteristics seen as similar to a stroke in a patient. Now, so the network will be divided into two halves, one controlling each of the two arms. Now, unlike the brain, in which the left half of the brain receives the information from the right half of the world and then controls the right half of the body, we're not going to assume this sort of a symmetry. We're just going to have the left half receive the left retinal images and the right half receive the right retinal images and control the corresponding arm. This is just done for simplicity. It does not actually have any impact on the output itself. Now, along with the input images, we will also be giving two hand selection parameters, which basically tells the network which of the two arms to move. These are just binary inputs, which is 0, 0. That is, do not move either arm. 0, 1, move only the right arm. 1, 0, move only the left arm. And 1, 1, move both the arms together. Therefore, by using this hand selection parameter, we can either make one or both hands active for a given target, thus operating the network on the unimanual or bimanual condition. By having either one or two targets in the input space, we can operate it in a bimanual joint or independent condition. If it is bimanual joint, there is only one target in the workspace and both the arms have to reach to that target together. Whereas in the independent, there are two targets in the workspace and the two arms need to reach to the target in their respective halves of the workspace. The performance of the system is measured using something called as reaching error, which is defined as the Euclidean distance between the target and the hand position. That is, the closest the hand can get to the target. These are the inputs that are used. We place the target in a particular XYZ position and then change both the size and the color of the inputs, thereby getting three different sets of images for the same target. This is done so that the network learns to only find or estimate the position of the target and does not get fooled either by the shadows or by the size or by the color of the target itself. And this is the architecture that we use. Here, the blue layers indicate the convolutional layers in the network, and the yellow layers denote the fully connected layers in the network. The right retinal image is given to the right half of the network, and the left retinal image is given to the left half of the network. In order to perform stereo vision, that is using 2D images to perform a 3D estimation and to be analogous to the layers in the brain, there are cross connections given between the two layers, between the two halves of the network in order to promote communication between the two halves. This is very similar to the role performed by the corpus callosum in the brain, which are just a bunch of fibers that connect the left hemisphere to the right hemisphere. These are present in both the first two of the convolutional layers and the first two of the fully connected layers. Now, the output from the fully connected layers are the 6 muscle activations that are going to be used by the arm in order to reach to the target. The hand selection inputs are given to the third convolutional layer on both the left and the right side. Excuse me. Now to this network. One second. One second. I'm sorry, my PowerPoint is not responding. I don't know why. Okay, I hope you guys can still see my screen now. So this point here, this thing here denotes a stroke. So in order to introduce a stroke, what we do is we again turn to the brain for what happens during a stroke. So during a stroke, due to the rupture or the stoppage of blood in one of the blood vessels, the neurons die. That is, they're no longer active. So to denote that, what we do is we get the activation from this penultimate layer of the network and then turn off some of the nodes and then send it to the output layer, thus effectively making it look like those neurons that were selected for the lesion are no longer active. Now, once the network architecture has been optimized, lesion is introduced in the penultimate layer of the network, just as I described previously. And only the lesion is only provided in the left half of the network in order to induce hemiparesis. Hemiparesis is nothing but paresis is basically weakness or paralysis in one side of the body, and hemi is basically denotes the one half of the body part. And 3 types of patient characteristics have been included in the network. Main point or objective of this network is to see if there is a correlation between the patient characteristics and the parameters that are going to be used to define the rehabilitation paradigm. So in order to do this, we included 3 types of patient characteristics, including lesion size, stage of recovery, and corpus callosal structural integrity. And similarly, we also use 3 parameters in order to define the rehabilitation paradigm. One was complexity of movement, hand selection mode, and the extent of plastic.
Yeah. Sorry to disturb. Yeah, I just wanted to understand. Can you show the previous slide again, please? Yeah, thank you. I just wanted to understand what's the task the model was performing. Like they were shown they were shown images, and how it's related to the movement of hands. I just wanted to understand like the task. So the task.
Sorry. So what here the point of the network is to look at the images and try to reach to the target that is placed in the workspace. So here the images will denote, it's actually stereo images. That is, I will place a target in a 3D workspace and take 2 images of it, similar to what happens in the eye. So there'll be two cameras placed. The distance between the two cameras will be similar to the distance between the two eyes, and those images will be taken, given to the network. Now the network will look at these two images and try to estimate the 3D position and then reach to that 3D position. That is what the output from the network will be.
Okay, yeah.
And
Now
do
I
you
understood.
use,
Thank you so much.
do you use robotic hands? I mean, how do you simulate that reaching part?
So we have the equations that need for, I mean, they're not, it's a completely computational model. It's not a physical system currently. So we know, like mathematically, we know the muscle activations that are going to be necessary to reach to those targets. So with that, I will generate the data set and then train the network with that generated data set. We'll be going through this in a more detailed manner during day 4 and day 5 in the project session for the bilateral networking. So there I will be showing how the equations work.
Just one more question. How do we understand that in which particular layer we have to create a lesion in order to understand the stroke?
Okay, so here with this network, I just wanted to see what would happen in a purely motor stroke. That is stroke in the motor cortex. So there have been multiple studies which show that the early layers of the convolutional network show a similar function to the early visual layers, which is why we decided to lesion the penultimate layer, the layer right before the output layer in the network, because we thought this would be more closer to the motor layer in the brain. So that's how we decided that.
Okay. Thank you so much.
No problem. So
Hello.
can I continue?
Hello, ma'am.
Yeah.
Is this the dataset of brain signal means EEG signal dataset or fMRI or any kind of dataset?
You mean the one that I use in the network?
Yes, madam.
No, the
During
one that I use is purely fictional. In the sense that if I have a 3D position, then using kinematics, I know the muscle activations or basically the joint angles that I will need to have my elbow and shoulder position in order to reach to that target. So using this, I create a synthetic data and use that to train the data. This network does not use any EEG or fMRI signals as of yet.
Okay. Ma'am.
I'll be going through the code in more detailed manner on day 4 and day 5. Maybe that will be a little bit more helpful. We'll also be releasing the code and the recorded lecture from during that time to everybody else. So anybody who's not going to be part of those things can also take a look at it.
Okay, thank you, ma'am. Is there any kind of demo that the experiment you have conducted? Any demo or kind of models there so that it could be very clear to us? Is there any kind of
Demo as in?
means the experiment you have conducted? So how this experimented worked?
Yeah, we'll be releasing the codes by the end of this workshop, so you should be able to understand it better then. So basically, this is okay. You can think about this as similar to the handwriting data set that Sir was talking about. So there's images of
Eminist
yeah, exactly. And there, the point of the network is to recognize what the images denote. So similar to that, here the images denote a position in the 3D workspace, and the network needs to now understand the location of that. So for that, I will be training this network. Does that make sense?
Okay. Thank you.
Okay.
Ma'am, can you explain this hand selection input? What does that mean? Just intuitively.
It
Those
basically
green squares.
so this basically just tells you which of the two hands to move. Like, for example, if you want to reach to a bottle on your desk, and you have both the arms on your desk, and the bottle is on the left side, then you know that using your left hand to reach to the bottle is going to be more easier. So that's basically what the hand selection input will tell you. That, hey, there is a target in the workspace, use your left hand to move to that, or use your right hand to move to that. So that's basically what the hand selection input will tell you. Does that make sense?
Yeah. Thank you.
Yeah. So these are the patient characteristics that we use. The lesion site that I already told you about, the penultimate layer will be chosen. And the penultimate layer has a total of 30 nodes. So out of that, 5, 10, 15, or 20 nodes are turned off. And we have two conditions called as acute and chronic. Acute stroke is basically less than or equal to 6 months after stroke onset. And the therapy is administered right after stroke is introduced in the network. Whereas in chronic stroke, in the patient, it means that more than 6 months has passed after stroke onset. In order to replicate this, we make the system, let's say I lesion the left half of the network. Now, in order to simulate chronic stroke, I will put the left arm in rest and only use the right arm over and over again. So because of this, there is more damage set up in the system because of non-use. Now, after this, the network will be taken to therapy. And then the other thing is CC structural integrity. Here, this is the CC or the corpus callosum. And now these weights are periodically removed from having all of the weights to having only half of it, or having only 70%, or having only 90%. This is done because experimentally it's been seen that the integrity of the corpus callosal structure plays a very important role in recovery. So next is rehabilitation paradigm characteristics. One is a stereotypic condition where the points only belong to a particular sphere in the workspace. This is meant to replicate the task-oriented rehabilitation, whereas in the other condition called exploratory, the points are distributed over the entire workspace. The number of points between the two conditions is maintained at a constant value. And the next thing is CIMT versus BMT. That is, move only the affected arm or move both the arms. And the third part is something called as the plasticity condition. Here, there is two types. One is local plasticity. That is, I will train only the weights that are attached to this particular network, called local plasticity, or train the entire network, again called global plasticity. So global plasticity is going to be definitely more computationally expensive than local plasticity. So the aim here is to see, even though it's computationally expensive, will the network prefer global plasticity over local plasticity, and under what conditions is it going to make this choice? This was the point of the study. Now, this is just a schematic to show exploratory versus stereotypic condition. And this is basically a picture of the enriched environment. Now, the local plasticity condition can be seen as containing only motor tasks. That is, raise your arm from 0 to 90 degree or 90 to 180 degree. Whereas in global plasticity can be seen as an enriched environment where there is multiple types of sensory stimuli, and you can use your arm as much as you want. So this is the effect of stroke in the network. So these are 3D plots, and each point in the plot basically shows the error that is experienced while reaching to the target. Under healthy condition, you can see that the error is extremely low almost across the entire workspace. But as I keep introducing lesion and as I keep increasing the size of the lesion, this keeps getting lower and lower. Now, this plot is the same plot, but in a different type. That is, these are the only points. That is, this plot only shows those points that are easily accessible to the arm. And you can see that this workspace keeps shrinking as the size of the lesion keeps increasing. So under acute stroke, I'm going to introduce lesion, etc. So we'll just move to the plots. So here I'm showing you what happens under different rehabilitation paradigms for different stroke conditions. And as you can see, there doesn't seem to be much of a difference between whether I'm using 1-0 condition or 1-1 condition. But there seems to be a difference when I'm using stereotypic versus exploratory condition. With exploratory condition almost always giving better recovery than the stereotypic condition. And this is seen across all nodes under both acute and chronic conditions. Now, with this in mind, here the structural integrity of the corpus callosum was maintained at 100%. So now we're going to see what happens when I start affecting this. When I start affecting this and I introduce the therapy here, I'm no longer seeing between exploratory and stereotypic because I've already shown that exploratory is going to be much better than stereotypic. So here the comparison is going to be between 1-0 hand selection condition and 1-1 hand selection condition under both local and global plasticity. For acute stroke condition, global plasticity is preferred over local plasticity when the lesion size is extremely high. But the picture is a little bit more complicated when the network undergoes chronic stroke. It's going to be more clear here. So under acute stroke, the network prefers global plasticity for a lesion size of 20 across all CC integrity conditions, whereas chronic stroke shows a more lesion size specific choice, where under 50% of corpus callosum structural integrity, the network only prefers global plasticity when the lesion size is extremely high. Whereas if the corpus callosum integrity is very high, then the global plasticity condition is preferred over local plasticity for all lesion conditions. Now, this could be because the corpus callosum is the structure that's going to allow the network to access the rest of the network. That is, one half of the network communicates with the other half of the network only through the corpus callosum. If that corpus callosum is compromised, then it can no longer use the resources of the other half. And hence, that's probably why only when the corpus callosum is at 100%, it's probably reaching out to the rest of the network. And that can be very easily seen in the chronic stroke condition. Thus, this network shows that complexity of the movement used is more important than the type of movement used. That is, debate should no longer be about unimanual or bimanual condition, but rather moving the therapies from a task-based rehabilitation condition to more exploratory rehabilitation condition. And the integrity of the perilesional area is extremely important for recovery and hence should not be ignored. That is, while imaging is used to see the site and size of the network, it should also be used to see how the integrity of the area right next to the lesion is going to be. And as the damage increases, the cost of the therapy also increases. That is, global is going to be preferred over local when the damage to the network is high. Some of the limitations of this network is that this is a very static network. That is, it can only perform reaching. That is, if I have a particular arm at a particular 0,0,0 position and I want to reach to, let's say, 0,5,0, the output gives the joint angles or the muscle activations required to reach to that. But this is not what happens in a normal hand. In order to move to 0,5,0 from 0,0,0, it's going to plot an entire trajectory. This is not considered in this network. Thereby, I'm saying that the network is static. So it can only model static impairments and it needs better muscular models also because it can only show impairment in degrees of freedom. That is, from 0 to 180 degree of normal elbow movement, the network after a stroke will experience maybe now a limited degree of movement. showing only maybe or reaching only maybe 0 to 50 degrees or 0 to 90 degrees. Whereas issues such as reduction in force, reduction in pressure, etc., which is also experienced by stroke subjects, is not seen by this network. The role of the ipsilateral hemisphere on recovery after stroke is not considered at all. Although this network now considers that the left half contributes to the left control of left arm and the right half uh, is used to control the right arm in the network, this picture is not that clear cut in the brain, where it's seen that especially in the higher cortical areas, both the halves of the network play a role in even unimanual and bimanual movement. This is not considered in this network at all and will need to be addressed in a future network. Only lesion in the penultimate layer is considered, and the other layers are left intact. And there is only a gross similarity between layers of the network in brain areas. More in-depth mapping with imaging and behavioral data is required for the network to more closely resemble patients. However, one good news is based on the results that we applied or that we got here, we developed a virtual reality gaming module which uses some of the insights that we gathered from this network. That is having exploratory versus stereotypic movements. And we actually did see that the games which utilized more exploratory movements actually contributed or correlated more with recovery than the stereotypic games itself. So that's it for my talk. If you guys have any questions, we can have them now.
Hello.
Yeah. Hi.
Yeah. Hi. So based on this work, any rehabilitation training protocol developed or not?
Yeah, so we developed a virtual reality gaming module containing about 5 games based on some insights that we gathered from this network. Now, one of the most important insight is that exploratory movements need to be encouraged. So we set up a spaceship type of game where the patients were allowed to explore what kind of gameplay they wanted to do and also what kind of movements they wanted to do. So they were allowed to play the game in any mode that they wanted to, versus a more stimulus response based game where there are balloons that appear on the screen and the patient needs to move to that in order to reach them. And we saw that the spaceship game was more closely related to recovery than the balloon based game. Now, the results are currently under analysis and we're wrapping up the study, but yeah.
Okay, so when we are developing such rehabilitation games or something, so for experimenting this one, we require some theoretical uh, uh, condition, right? Okay, we can apply this one for patients.
Yeah.
So
So
who is
we got ethical clearance from both our institute side and from the hospital side. And we also had doctors on board who helped us design the games, everything. It was actually a 4 institute study with IIT Madras, IIIT Hyderabad, Sri Chitra Tirunal Institute in Kerala, and NIMHANS Bangalore. So we had doctors and stroke experts on board when we designed the game. And currently, the pilot study is done, and we're still looking at getting the regulatory certificates in order to market it in a more um, global scale.
Okay, thank you.
Thank you. Any other
Hello.
question? Yeah.
Hello. Yeah,
Yeah.
thank you so much for this wonderful talk. I just wanted to ask one question. I was just finding a bit hard to understand global plasticity. Like, as you mentioned that if there is a large, like,
Yes. Hello. 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 Hello, can everyone else hear me?
Yes. Hi, Sundari. Yeah.
Oh, okay, okay. I don't know how many of you will be joining me on day 4 and 5 for the project, but there we'll be seeing a little bit of a different network where just because we have only 2.5 hours, I'll be using a MLP model instead of a CNN model just because it makes training a lot more easier. Yeah. We use the penultimate layer only because I think, like I said, the convolutional layers are expected to denote the visual layers, and the fully connected layers are expected to denote the the fully connected layers are expected to denote the motor layers. And this is the reason why we choose the penultimate layer because I wanted to only study how a motor stroke is going to create an issue. That is a stroke purely only in the motor layers of the brain. Because what happens is sometimes, because of the location of the stroke, people have comorbidities, which is not just a movement related problem. They could also have other problems. But because my study was purely a motor related study, that is the reason why I chose the penultimate. We want to put this in a portable stroke rehab device. Can I buy CNN on a small chip or does it need it? No, it can run on a small chip. It's not that computationally heavy. It's just that 2.5 hours is not enough. That is the only reason in the session we'll be using an MLP, but it can run on a small chip. It doesn't need a full GPU. It's not that heavy computationally.
In day 4 and 5, can we just observe the projects which we are not allotted? Like it happens at different time, no? So will it be possible?
Yeah, you can attend, but it's up to you. If you don't feel exhausted, then sure. But we will also be sending the recorded lecture, and the code books will be available for all the participants in the workshop, not just the um, specific project core group.
Okay.
Hello.
Yeah, hi. I think I lost you before.
Yes. My network got disconnected. So my question was that as you mentioned that greater the lesion, then it preferred global plasticity. I just wanted to understand how do we see that thing from a biological point of view? Like what is happening inside the brain if the lesion size is greater than what does it mean by global plasticity?
Okay, so actually, this graph, more than let's say the lesion size is higher, you need to concentrate more on the structural integrity of the corpus callosum. So what happens in the brain is if you have the corpus callosum damaged because of the stroke, it's not going to be able to access the resources in the other hemisphere very easily. So even if the other hemisphere tries to help this hemisphere in recovering or by sharing the higher part of the load in making the affected arm move, because of the damaged corpus callosum, the activation is not going to be able to be passed from one half of the brain to the other half of the brain. So because of this, the using or having global plasticity type training is not going to be useful for the patient. They're not going to recover better than local plasticity. So it might make more sense for them to just stick with local plasticity because at least in terms of the network, the computational network, the resources that are going to be used is lower. So we can't make a general statement that anybody, if you give a globally rich or a enriched environment therapy, they will recover uniformly. No, it will highly depend on the structural integrity of the corpus callosum. That is one of the main points of this graph here.
Okay, yeah, now I understood. Yes, thank you.
Okay. Any other questions, or can we close the meeting? Can we pre-train the CNN on healthy people first and then just fine-tune it for stroke patients? Yes, that is actually what we do anyway, even in the network. We train it as a healthy network first and then introduce a stroke to see how it's going to be affected because of the damage. Okay, if there's no other questions, maybe we can close the session and we can.
Hello.
Yeah, hi.
Yes, ma'am. Ma'am, can you please tell us how the projects will be carried out? Means, is it the individual project or is it the group project or
Okay,
what?
so it will depend from the TAs who are handling it, but mostly, so there's about 68 participants who have been registered. So each of the 4 groups will get about 17 participants. So from that, if the TA chooses, they can either have the participant all do the same project, or you'll be divided into 2 or 3 groups and then like placed in different breakout sessions, and you'll be given a small mini project which you can just slightly modify the code and try and see, run and see and how the response is going to change, and then you'll again come back in the bigger group and discuss the results. That's mostly how the project is going to be. So for the bilateral network thing, the what I'm planning on doing is give uh, like basically separate them into 4 groups and see how a different type of therapy is going to work for a different kind of lesion condition, and then they'll all come back into the bigger group and discuss about that. So that's how it's going to be set up.
Okay, for oscillator network model of fMRI, is this a different TA or some
Yeah,
other?
yeah, and you'll be meeting him tomorrow during the practical session. Like in the later half of the day, he'll be giving a demo on XPPOT about how to perform phase plane analysis and stuff. So yeah, he'll be taking the oscillator network stuff.
Okay, thank you, ma'am.
Okay. Okay, if there's no other questions, I think we'll conclude the session for uh, the forenoon part of today. We'll meet again around 2 o'clock for the practical session. Kindly be on time so that we can start it on time. That's also going to be really fun. They're going to talk more about how deep neural networks can be used to both in auditory and visual systems in the brain. And yeah, so we'll see you guys then. Thank you. Bye-bye.
Thank you, ma'am.
Thank you.